Vertical acceleration of a parcel. If we use the general equation of motion for a parcel with a density ρ dashed, then the force ρ dashed by dw dash dt is equal to the pressure gradient minus dp dz minus the weight of the parcel minus ρ dashed by g. If we divide through by ρ dashed, we end up with dw dash dt. The acceleration of our parcel of air is equal to minus 1 on ρ dashed dp dz minus g. We can use the hydrostatic approximation. dp dz is equal to minus ρg, where ρ is the density of the environment, and when you do that and rearrange the equation slightly, you end up with the buoyancy equation for a parcel of air is equal to g divided by ρ dashed, the density of the parcel, multiplied by ρ minus ρ dashed, which is the difference between the environmental density and the density of the parcel. So, for example, if a parcel is less dense than its environment, then the acceleration will be upwards. If it's more dense than its environment, then its acceleration will be downwards. And if the density of the parcel and its environment are the same, there will be no net acceleration. Note throughout all this that the parcel always adjusts to its environmental pressure. So here's our equation. And I've more or less said this already. When a parcel has a density that's less dense than the environment, then a small displacement upwards will give a positive net acceleration. And so we say that's unstable equilibrium. A small vertical displacement results in upward motion of the parcel. When ρ dashed is more dense than its environment, a small displacement upwards will result in a negative net acceleration. So it's a stable equilibrium. We typically prefer to work with temperatures, and so we can use the ideal gas law that ρ is P on RD TV, where TV is the virtual temperature. And when you do that, and I'll leave that as an exercise for you to do, you end up with a buoyancy equation, dw dash dt is equal to G divided by TV, which is the virtual temperature of the environment, multiplied by the virtual temperature of the parcel minus the virtual temperature of the environment. So when the virtual temperature of the parcel is greater than that of the environment, then we have positive buoyancy. The parcel, after a small vertical displacement, will move upwards. But if after that small vertical displacement the parcel's virtual temperature is less than that of the environment, then the buoyancy force is downwards. And if the vertical displacement means that the parcel's virtual temperature is the same as the environment, then there's a neutral buoyancy. So what have we done? In the preceding development, we've used parcel theory assumptions, and we've assumed that in case of saturated ascent, there's no reduction in the buoyancy resulting from the weight of the liquid water in the parcel, since all the water is rained out. So it's an irreversible process.